In this video, we have a problem here where we're asked to find the gravitational force exerted on the Earth by the moon and by the moon on the Earth. So just looking at that, we can see that there's going to be a Newton's third law pair, an equal and opposite force on both bodies. It's going to be a gravitational force. We're asked to express our answer as a vector and use the given quantities below. So we have the mass of the Earth, that's m sub e, equal to 5.97 times 10 to the 24th kilograms. And then we have the mass of the moon is 7.35 times 10 to the 22nd kilograms. And that difference there of two factors of 10, where the mass of the Earth is 10 to the 24th, and the mass of the moon has this factor of 10 to the 22nd, we say that's a difference of 2 orders of magnitude. Those two factors of 10, the difference between 10 to the 24th and 10 to the 22nd, we say that's a difference of 2 orders of magnitude. So that's just for your information. And then we have the radius between the two bodies is 3.80 times 10 to the 8th meters. So let's start with a picture. We're asked to express these answers as vectors, so we're going to have to define some directions. So I'm going to start here with the Earth, and then I'm going to also draw a smaller body over here to the right, and this will be the moon. Obviously the moon is smaller, and so this is my Earth, and this is the moon. And I'm going to define the direction towards the right as the x-hat direction, and this is going to be positive. So this will be the positive x-hat direction, and to the left will be the negative x-hat direction. So we're asked to find the force exerted by each of these bodies on one another. So we're going to have a force of the Earth on the moon that we're needing to find. And we're also looking to find the force of the moon on the Earth. So we want to find these two quantities. And with what we're given here now, we can use Newton's law of universal gravitation, the formula, to find these forces. We have two masses and we have this distance between them. So just to review, the formula is the gravitational force is equal to the gravitational constant, capital G, times the mass of the first object times the mass of the second object, all over the radius squared. And this is going to be in the r hat direction, where r hat is the vector pointing from one object to the other object. So we can define r hat as x hat or negative x hat, since that's how we've defined our directions here. So we're going to be using this formula. Okay, and then what is g? So the gravitational constant is just a special number that is true for any force of gravity between two objects. It's going to have this factor of g is equal to 6.67 times 10 to the negative 11th, so it's a small number. The units then are meters cubed over kilograms times seconds squared. And these units, when we plug them into this equation here, are going to resolve all of these units here for the two masses. This is 2 units of kilograms, and then we have this distance squared, so that's going to be meters squared. And when we put this unit here for the gravitational constant into the force of gravity formula, it's going to resolve all those units, and so all we'll have left is newtons. And so now I can calculate the force on these two objects, and I know that it's going to be equal and opposite for both these objects. So this will be the force of the moon on the Earth. And then we're going to have an equal and opposite force that is pulling on the moon. I'm going to try to draw these the same length. So both these vectors are supposed to be equal and opposite here, the same length. And this will be the force of the Earth on the moon. So all I need to do is figure out one of these, and I'll know that the other one is just the opposite sign, and that's due to Newton's third law. So let's figure this out then. So I'm going to find the force of the moon on the Earth. I'm using this formula here for Newton's law of universal gravitation, and now I'm going to first plug in the number and the units for the gravitational constant. So that's 6.67 times 10 to the negative 11, and that's meters cubed over kilograms times seconds squared. So that's G. All right, so M1 is the mass of the moon. So I'll put in, now this is going to be, I'm going to use some parentheses here just to break this up. So this is going to be 7.35 times 10 to the 22nd kilograms. So that's mass 1. Mass 2 is going to be the mass of the Earth. That's 5.97 times 10 to the 24th kilograms. And all of this is going to be over the distance between them squared. So I'm going to draw my fraction bar here. And then I'm going to put these in parentheses. So the distance between them is going to be 3.80 times 10 to the 8th meters. And all of this gets squared. So I've plugged in everything here for the formula. I've got the gravitational constant, I've got the two masses, and I've got the distance squared. And now I can start resolving all of these different units and the numeric values. So I have a kilograms here. I'm going to cross that out because I can divide a kilogram by a kilogram, so that's 1. And then I have this meters is actually squared. So I have a meters cubed over a meters squared. So what I'm going to do, I'm going to cross out this meters squared. I'm saying it's a meter squared because it's in the parentheses and it's squared. And then I'm going to cross out this exponent of 3. And I'm going to draw an exponent of 1 just to remind myself that that is an m to the first power. And what am I left here? I have kilograms, meters, and seconds squared. And I know that I'm trying to get to newtons. And a newton is defined as 1 kilogram times 1 meter per second squared. So accelerating 1 kilogram at 1 meter per second squared. Well, I see I have my seconds squared in the denominator, so that's good. And I have my 1 factor of meters, and then I have my 1 factor of kilograms. So my units are good. And I can actually rewrite these here. I have meters times kilograms over seconds squared, and this is just newtons. So my units are good. I've done my unit analysis, and I've gotten exactly what I needed, which is newtons. Now I have all these numeric values and these exponents. So the way I would handle this is I would try to combine all my numeric factors that aren't 10 to some power. So I would combine all my 10 to the 22, 10 to the 24th, this 10 to the 16th, because it's 8 times 2, so this is 16. So let's do this over here. I'm going to do some side work over here. So I have a 10 to the negative 11th times a 10 to the 22nd times a 10 to the 24th. All of this is divided by a 10 to the 8th squared. So this is 10 to the 16th. We have to remember our exponent rules. If you have an exponent raised to a power, Well, this is the same as 10 to the 8 times 2 power, which is 10 to the 16th. Now, for these other exponents on the top here in the numerator, these will just be added together. So that's just another exponent rule that we have to remember. So we have here a 10 to the negative 11th times a 10 to the 22nd. These two are actually 10 to the 11th. So I've just added a 22 and a negative 11. That gets me a 10 to the 11th. So then this becomes 10 to the 11 plus 24 is 10 to the 35 over 10 to the 16. And if we have exponents, one in the numerator and one in the denominator, well, now we take 10 to the 35 minus 16, and that is going to be, let's see here, so this becomes 10 to the 35 minus 10 is 10 to the 25. 10 to the 25 minus 6 is 10 to the 19th. Now, all of these I just did in my head using exponent rules. If I have two exponents with the same base and one is raised to a power, then I have to multiply those two. So that would be 10 to the 8th times 2 is 10 to the 16th. If I have the same base and different powers and they're multiplied together, not raised to a power, but they're multiplied together, then you add the exponents. If you have the same base and you're dividing them, well, then you subtract the denominator from the numerator and you get your answer. Now, if all of this, if you're not comfortable with your exponent rules, or if you just need to check yourself, just plug these into a calculator and be careful using your exponents. If you're using a graphing calculator, you should be able to use your exponents even if it's a negative exponent, and you should be able to get your correct answer. So this 10 to the 19th is my one piece of this force. So now I have the force of the mass on the Earth, and now all I have left are these numeric values. So I have this one, 7.35, and I have to remember this 3.80 is squared. So I have this one. So now I can combine these together. So let's see what I have here. I have a 6.67 times a 7.35 times a 5.97 divided by, the only one in the denominator now is this 3.80 squared. So this is 3.80 squared times a 10 to the 19th. And my units I found were newtons. Okay, so that was a bit of work. I had some side work here just to figure out these powers of 10. You could just put in everything I had here in this first step right here. If you were very careful and put all of that into a calculator, then you would get the correct answer. But it's a lot to plug into a calculator. That's a lot of numbers and powers of 10. So I like to resolve the powers of 10 separately and then work on these numbers. These other numeric values then I can plug into my calculator. So I have a 6.67 times a 7.35 times a 5.97 divided by 3.80, and I have to remember to square that. And to two decimal places now, I have, this is equal to 20 point, to two decimal places, 27, and that is times a 10 to the 19th newtons. And since we're using scientific notation, I want to express this as one number in front of the decimal symbol. Just like all these other numbers were given to us as 5.97, 7.35. I want to now express this with just one number in front of the decimal place. If you didn't do this, it would be fine. I'm doing this because this is how this problem was presented. We have one number in front of the decimal place. That's how we show numeric values with scientific notation. So if I shift the decimal place to the left, then this becomes 2.027. And if this number got smaller, then to keep it equal, now this number, the power of 10 has to get larger. I can't just shift this number to the left without balancing out. If this number here gets smaller, well then this number has to get bigger for it to stay the same number. So now I have 2.027 times 10 to the 20th newtons. And that is my magnitude of the force between the moon and the earth and the moon. But we're asked to express our answer as a vector. So I'm not quite done yet. I have the magnitude. This is the magnitude of the force of the moon on the earth, and also the magnitude of the force of the earth on the moon. So to express these as vectors, now I have to see, okay, I've got one pointing to the right, that's the force of the moon on the earth. So for the force of the moon on the earth vector, I need then my magnitude, which is, I'm going to round this down now to just 2 decimal places. So this is going to become 2.03. I'm just shortening this by rounding it down to 2 decimal places now, just like all the rest of the numbers given to us, times 10 to the 20th newtons. And what is my direction for force of the moon on the earth? Well, that's going to be in the positive x hat direction. So that's my one answer. I have the force of the moon on the earth vector, and it's pointing in the positive x hat direction. And then, like I said earlier, we know these magnitudes are the same, and we've defined our coordinate system to be the positive x hat pointing to the right. Well, then this force of the earth on the moon is pointing in the negative x hat direction. So the force of the earth on the moon vector is the same magnitude. I'm just rounding down to 2 decimal places, times 10 to the 20th, and that's newtons. Now I'm going to say it is pointing in the negative x hat direction. And those are our 2 forces. And again, this is a Newton's third law pair. So it's an equal and opposite force. And what does that mean? So the Earth and the Moon are obviously different masses. The Moon is much, much smaller than the Earth. But the forces are the same. So just like we learned with when we were introduced to Newton's third law, and we said, well, you know, if you're driving down the highway and you're in a large vehicle and you hit a mosquito, well, the force of the mosquito hitting your windshield and the car hitting the mosquito is the same. But the accelerations are very different because, according to Newton's second law, F equals ma. So if the forces are the same, well, the masses are clearly different between a small object and a large object. So for the forces to remain the same, if you increase the mass, then you have to decrease the acceleration. And for the same, if you decrease the mass, then you have to increase the acceleration. So the moon is going to have a larger magnitude of acceleration pointing towards the Earth because of its smaller mass. And so this is how Newton's universal law of gravitation can be used to show the gravitational force between any 2 objects. It's very powerful, and it can be used on any 2 objects anywhere in the universe at any distance apart.